Welcome to this short little video segment on how we use Ampere's law to find an expression for the magnetic field inside a solenoid. You might remember that a solenoid makes a nice uniform B field inside as long as we have a nice tight coil and we stay fairly close to the middle, not too close to the edges. It's important that you know how to apply Ampere's law in this situation, as well as the other common situation, which is the long straight wire, which is demonstrated in your textbooks and probably most textbooks besides. So let's take a look at how this works. I'm going to start by writing the expression for Ampere's law. And whenever you're asked to use Ampere's law for something, it's always important to write the expression down. And it starts on the left side with a line integral. It's the integral of b dot ds. B and ds are both vectors. You put a little circle around the integral sign that reminds you that it's an entire closed loop. And on the other side you've got the permeability constant mu naught. And then you always write I and a little subscript that tells you that you're only going to consider currents that are going through a little path. So we call this an Amperian loop, or it's labeled on this diagram as an integration path, because every time you use Ampere's law, you have to make a little path around a closed loop. And the B in the left side of the expression is the magnetic field at any point on that path. And the ds is the small little step along the path that you take as you circulate around it. And then the other side has mu naught, and the I is all of the current that is going through that loop. So in this particular case, we always draw a rectangle, and it's a rectangle that has one of its sides inside the solenoid, the other side outside the solenoid, and then the other two sides kind of connecting those. So I've just grabbed an image off of the internet here and used it because it's drawn so nicely. Now what we'll find out is it doesn't matter how long we make it, so that length there, L, makes no difference at all. But as long as one side is inside the coil and the other side is out, we're going to be fine. So what do we get as we go along this path? Let's just start at letter A and go around all four sides, and we'll write an expression for the b dot ds for that side. So as I traverse along here, going from A to B, that's my first path that I drew there in blue. Well, what is the b dot ds integral there? Well, B, because B is uniform everywhere inside there, then at any point along that side I'm going to get the same value. So I just can consider that like pulling B out of the integral and summing together all the steps I take across there. Well, that's going to give me a total of B times L, just for that side. And then let's continue around the path up the left side here, between points B and C, and what do we get there? Well, as long as we're here inside the solenoid, we have a B field to measure, and we have a little step to measure. But notice that the dot product here would be 0 because my steps are always going to be perpendicular to the actual B field. So that means I'm going to get a total of 0 there. And then once I go outside the solenoid, I'm going to get 0 because I have no field out there. So it doesn't matter how many steps I take. Similarly, along the path from C to D, there's no field there either. So I have to add another 0 term. And then along the path from D to A, very similar to going from B to C, I either have no field at all, or my field is completely perpendicular to my steps. So by the time I'm back to where I started, I've just added 3 more zeros. So that means the total on my left side is just B times L. Now let's go to the right side, where we have our mu naught. Then we're going to need some expression for the amount of current that is going through our little integration path, or our Amperian loop. Now do you see that that's going to depend on how long of an integration path we drew, that dimension L there. So how are those related? Well, Notice that we're only showing part of the solenoid, the central part here. But there is a solenoid that is, much longer than this. And I don't know how long it might be, but perhaps it goes that long. And let's just use a small case L for that. So the number of coils that we've actually picked off by our integration path is related to how much shorter capital L is compared to small case L. And so what that means is if we know the total number of turns in our solenoid, we're going to call that capital N, then the number that's actually inside the integration path is just that number times the ratio of how big L is to little l. So if we know that's how many turns are actually inside the integration path, and each one of them has some current that I'm just going to refer to as I. That's like what the little x here would be indicating. So, and it's the same current just looping around and around and around. So then that total is the total current going through there. In this case it's 8, but there's nothing magical about the number 8. So what happens here? Well, we have an L on the left side and we have an L up here on the right side. And so when we cancel those out and solve for B, we get this expression mu naught times N over little l, the length of the solenoid, times I. And this is most commonly written mu naught times little n times I, where little n is called the coil density, how many turns you have per length of solenoid. So you'll see it two different ways. And in that way, I hope you can tell that the length of our integration path, how wide that rectangle was, made no difference whatsoever. So that's how we get the expression, and of course that's a formula you could just think to memorize, and you could do that, but I want you to be able to, and anybody teaching Ampere's law expects you to be able to use Ampere's law from the beginning all the way through like I did there to derive an expression for the magnetic field inside that solenoid. So I'll leave it at that. If you want to look at more details on this, you can find lots of references in your textbook and other places besides, and of course you can always find me to ask me for help too.